So for a constant N, V, and T system, we saw that when the system reaches a minimum in its Helmholtz energy, it is at equilibrium then. Okay? And so what we're going to look at now is a system in which we have constant N, constant pressure, and constant temperature. For this type of system, what you can imagine is that you actually have a piston cylinder sort of setup. Okay? Where your system is inside the piston cylinder. Outside the piston cylinder is some sort of reservoir at temperature T. Heat transfer between, and there's heat transfer between the reservoir and the system, and can be in either direction. And the setup we have here is that the volume of the system can change, but the force acting against the system, against its expansion or its contraction, is going to be constant. And so we know that from the force balance, if that force acting against the gas is constant, that means that the pressure of the gas will also be constant. Okay? All right, and so this is the basic setup for a NPT system. And so to identify its equilibrium criterion, we once again will look at the universe, which is the system plus the reservoir. And from the system energy balance, the change in the internal energy of the system is now not only going to have a heat term, it's also going to have a work term, a mechanical work term, a P delta V. If we rearrange this equation, so we have U sys plus delta PV, and so what I did here is, since P is constant, we could move it inside the delta. Right? What we then have, because we know that delta U plus delta PV is just delta H, we then get that the delta H of our system is equal to Q total. For the entropy balance, that's still going to be equal to, we'll just say it's some delta S. For the reservoir, its change in internal energy is just going to be equal to Q total, right? Because while the system volume is changing and things like that, the reservoir is so big that even if the system changes volume, the reservoir is not like affected by that volume change at all, right? The reservoir is not expanding or contracting. Okay, so it doesn't have a significant work term. And so the delta U of the reservoir is just going to be delta U is equal to negative Q total. There's just a heat term. All right, for the entropy balance for the reservoir, we have delta S res is equal to negative Q total over the temperature at the boundary between the reservoir and the system. We know from the energy balance on the system that Q total is just equal to negative delta H of the system. When we take a look at the change in entropy of the universe, we have delta S of the system plus delta S of the reservoir, which we know is just delta H of the system minus T. Rearrange the equation. what we have here, if I move this entire line down a bit, once again, if we remember back to our Legendre transforms, we recognize that delta H minus T delta S is just delta G. And so what we find is that the delta S of the universe is going to be equal to the negative delta G of our system. And those things have to be greater than or equal to 0. So for an NPT system, what we find is that our delta G, delta G decreases for spontaneous, irreversible processes. And when the entropy of the universe is maximized such that delta S of the universe is just equal to 0, what we find is that the Gibbs energy will reach a minimum, or will be at a minimum.